So I've got a request from you. If you will watch the video that I was going to present today, it's on Blackboard already. It's the one on the introduction to vibrational spectroscopy. Then we can spend the whole day reviewing. But it's this for that, right? I'll do the review today if you'll watch that video and go through the notes and everything like that to get ready for the next section of the course. Does that sound like a deal? Okay, great. So this is going to be a lot of Q&A. I've got all of the homeworks loaded up on this one, so you can ask me about any of the questions that you have on the homeworks. The exam's going to be very close to those homework assignments, and so it should prepare you very, very well for what you're going to see. Okay. So with that, give it to you guys. What questions do you have? Yes. Number 4? Okay. Okay, so this is for benzene. And so over here on the right, we have the D6H character table. It's a little small on the screen, but what we're looking at, so the irreducible representations inside the transition dipole moment integral for the transition from the E1 state to an A1G state with X or Y polarized light. So those are the 3 pieces. So we're going to an A1G, okay, and then we have X or Y polarized light. So we go down in the character table and we find that right here. So since those are coupled, it would work for X polarized light or Y polarized light. And so that's going to come in as E1U. And then this is saying from an E1U state, so the lower wave function is E1U. So those are the 3 pieces. Then we can use these direct product tables down here. So let's go ahead and do these. So E1 times E1, so anything times itself is going to be A1. Does everybody know that? Anything times itself is going to be A1, but it might have other things associated with it. So let's go ahead and look. Here's E1 here, and here's E1 here. So it's got these 3 things, A1, A2, and E2. And then the U times U. So we have to use these general rules right here to do the U's and G's. So U times U is G. So these are all G's. What's that? Oh yeah, you'll have to have you have to have the direct product table and the character table to be able to do this, especially for something as complicated as benzene, right? Yeah, well, the one on this exam is you're gonna be given the point group for the one that you do this. So it's not like you could get the wrong point group and have the whole thing wrong. So I'm saying for this molecule and this vibrational motion, then what's the allowed transition, that kind of thing. And you'll have the character table for that particular molecule, so you can't mess that up, and the direct product table for that molecule. So I was nice to you on that one. And then A1G over here. Okay. Now A1G times anything is going to just give you that thing. Okay. So then this times all of these is just going to give you those back. So we're going to have A1G plus A2G plus E2G. So that's inside that integral. And so that's what we mean, what the irreducible representations inside the transition dipole moment integral. So after we do the direct products, this is what we have. And so this is what we here, it's this one. A1G plus A2G plus E2G. Okay. Now then, let's see, does it ask you this question? Which one, will this transition be allowed? So that's a question I didn't ask on the homework, but it's right here. So you nodded your head real quick over here. Why? Why is that? Contains A1G. Yeah, so this right here is what you're looking for. That is the top row of the character table. So that's the only even row And so if a function has that symmetry, when you integrate over all space, it'll be non-zero. These other two will be zero. So this integral is not equal to zero. Therefore, it's allowed by symmetry. Okay, so that's the conclusion that you would have for that. Good question. Who's next? Picture. Is that an octopus? What is that? Yes. Sorry. Number 19 on the same homework. 16, 18, 19. Oh, it is? Oh, okay. Yes, for sure. And so that's why we're going over this today, for sure, to make sure you guys know it. So even though that's not due till, I guess, Saturday, we'll go over all the answers here. So if you have any questions, yeah. So, quiz 5. Let me look. Let me pull that one up. It's going to be a lot of dead air on this video. Okay. Quiz 5. I don't know why that's not on the PowerPoint. Let me just grab it real quick with a snipping tool. Just bear with me on a second. I'll get to it. There we go. Okay, I know it's hard to see, but I'll go ahead and tell you which one. So you're asking about 19, which says, what's the major difference between that one, the 631G and the 631G DP basis set? So let me write it out a little bigger. So we're looking at 6-31G versus 6-31G with D and P. And the options are diffuse functions on heavy atoms only, diffuse functions on both heavy atoms and hydrogen, higher angular momentum functions on heavy atoms only, and higher angular momentum functions on both heavy atoms and hydrogen. Okay. So this D and P are related to what we call the orbitals, right? So just the quantum numbers, there's the principal quantum number, which is equal to n, right? And then there's the angular momentum quantum number, which is equal to L. And when we're talking about all of these quantum numbers in freshman chemistry, and also I guess when they decided to come up with these, the L quantum number starts at 0 and goes all the way up to n minus 1. And so if we have a principal quantum number of 4, then L can be 0, 1, 2, and 3, because it can go up to n minus 1. So 0, 1, 2, and 3. We've given those letters. So if n equals 4, L equals 0, 1, 2, 3. And we've given those letters. That's S, P, D, F. So this is review, but right there, that ties these letters to this idea of angular momentum. Okay. And so this D and P should, in your mind, always be associated with angular momentum. So that's a way to remember that. We're talking about higher level orbitals. So higher angular momentum in the way these electrons go around the atom or the molecule. If we want them to have more nodes as they go around, like a p orbital has nodes as it goes around, but an s orbital doesn't. So a p orbital has more angular momentum. A d orbital has 4 nodes, or 2, I guess, as it goes around. And so that has even more angular momentum than a p orbital. So those d and p designations in this basis set are meant to kind of clue you in that you're adding more angular momentum and more flexibility in direction to the electron. So that would be more angular momentum. The comma separates heavy atoms and hydrogen. So the first one is heavy atoms, and the second one is hydrogen. So in this case, on the right, we're putting d orbitals on all atoms except hydrogen, and p orbitals on hydrogens. It's important if you have hydrogen bonding, like if you're trying to model 2 molecules that are making a hydrogen bond, hydrogen bonds are directional. And so in that situation, you'd want to put a p orbital on their hydrogens so they have a directional angular momentum, and that will assist the energy of the molecule to find a better geometry. So that's the major difference between these 2 basis sets. So whenever you do a homework problem, you've got 4 choices here. You find the right choice. It's this last one here. A higher angular momentum functions on both heavy atoms and hydrogen. So that's the answer. Now, the non-thinking P-Chem student would say, great, I got the answer, I got the points, move on. The thinking P-Chem student says, what are the other 3 options? And how might DW ask a question that would make them the right answer? Okay, so what would be a basis function where it's just angular momentum functions on the heavy atoms? Right, so 6-31 GD. So only D functions on the heavy atoms, no comma P. So that's just heavy atoms. What about the diffuse functions on both? It's typically put right here, plus G. Or is it G plus plus? I have to go back and look. But anyway, the pluses, these are the diffuse functions. Okay. And if there's 2 pluses, it's on both heavy atoms and hydrogen. If there's just 1 plus, it's on heavy atoms. Okay. So this one here, the first option was just heavy atoms only. 6-31. Maybe it's after the G. I don't remember. But anyway, this is the main thing. That plus. So the plus, you could be thinking of a plus as sort of adding more s orbitals, because the s orbitals, as you go up in quantum number, they get bigger, they go further out. And so this allows the electron to have a further distance from the nuclei, and the d and p orbitals allow the electron to pick particular angles that they can bond with. Good question. Let's see. I think it was Cheyenne. You had a question, but when I went with him, what was it?
Can you work through the questions that go with figure 1 from quiz 6?
Okay. Trying to find it. Is this it?
Yes.
Okay. Okay, so we have up here the wave function and the wave function products. And so here, it's a little hard to see on the screen, but this blue is psi 1, and this blue is psi1 squared. So the symmetry of n equals 1, or wave function 1, is, and so we look at that and we go, like we start at the origin, we go to the right a certain distance and go evaluate the wave function, and it's a positive number. We go to the left the same distance and evaluate the wave function, and it's the same number. So that means it's even. So the n equals 1 is even, and n equals 2. If we did that and evaluated it, it would be down here. If we went left and evaluated it, it would be up here. It's the same magnitude but opposite sign. So that would be odd, definition of odd. And you can see that in the function when you look at the picture. Just sort of look at where 0 is, and is the left side the same, or is the left side a mirror image of itself, like a -1? So if it's a perfect mirror image, the left and the right side look the same, then it's even. If they have the same shape but opposite sign, then it's odd. So you can see the red curve or orange curve. It's positive on one side, negative on the other side, but the same general shape. That's an odd function. If we were looking at a molecular orbital, those would be different colors. So like this might be shaded and this might be open. And so we would see that going left, it's shaded, going right, it's open. It's an odd function. Whereas the green one, or the blue one, would be shaded all completely. Let's just say that, so this n equals 1 would be all shaded, and sometime later it would be unshaded. Okay, so now the symmetry of wave function 1 times itself is, so we have an even function times an even function, so it's going to be even. And the symmetry of wave function 1 times wave function 2, we have an even function times an odd function, so this is the product of psi1 times psi2, and you can see that it's odd. And then the integral of wave function 1 times itself. So we're looking at this blue curve. If we integrate this curve right here, so we take the integral over all space, which is the x-axis, of psi1 squared dx, that is going to be not equal to 0. Can you see that? So if we take the area under the curve, it's non-zero. Whereas this orange one, if we integrate over all space of psi1 times psi2 dx, that's going to be equal to 0 because we've got some positive numbers here and negative numbers there. And when we add up all of them, the negatives are going to cancel the positives, and we end up with 0. So this one is going to be is not equal to 0, and the integral of psi1 to psi2 times psi2 is equal to 0. When you integrate it. Yeah, so that was the whole point of the symmetry. So when we go through the symmetry, and even in three-dimensional space, like we just did with the benzene, we had an A1G, we had a bunch of other stuff. The integrals of all those other things will be 0. Because whenever you have this plus that, you can make 3 different integrals. So the integral of all of the odd ones equals 0, but that A1G is non-zero. So then that transition is allowed because there is an A1G piece. And it's not always A1G, it's just whatever the top row is. So like in a C2V molecule, like water, it's just A1. There's no G's and U's. Here's a question for you. When do you have the G's and U's? What kinds of molecules, or they have to possess a particular symmetry element. So what are the symmetry elements? E, the identity, the C2 or CN axis, an SN axis, a mirror plane, or an inversion center. So those are your 5 symmetry elements. One of those symmetry elements will tell you if you have G or U in your point group. Carry. So the answer to that question is it's the inversion center. So if it does not have an inversion center, it won't have G's and U's. But if it does have an inversion center, then you have G's and U's. And that's why the benzene problem that we looked at, let's see, is that up or down? Yeah, see here, the benzene problem, D6H, right over here is the inversion center. And notice all of the top part of the table is the G's. A1G, A2G, all of those G's. Bottom part of the U's. What do we see on the top part of the table? The inversion. They're all positive under inversion for the G's, and they're negative under inversion for the U's. So that's what determines even an odd inversion symmetry is that inversion symmetry element, and that tells you if it's a G or a U transition. So I'll show two orbitals that have, like let's look at like a p orbital, right? A p orbital looks like this, and it's shaded on top. And if we did the inversion of that, okay, so we would take a point here and go through the center of mass to the other side, the exact same point on the other side, and you see it's changed color. It's now shaded. And so that's equal to minus 1 because it changed sign. So this orbital is going to be down in the U section of this character table. Now, p orbitals are like px and py, and so here's the x and y ones. There's also a pz, and here's the z one. So the p orbitals, by definition, they have to be in the U area of a character table that has an inversion center. So at D6H, the px and py orbitals would be down here, A2U or E1U. What about, say, the d orbital? So dxy. It looks like this. It's got a positive, a negative, a positive, and a negative. Meaning it's expanding in those corners and contracting in the other corners. At some time later, it does the opposite. So if I pick a spot here and I do an inversion, I go through the center of mass to the other side, it's still the same sign. And so that would be a +1. So if I did an inversion operation on this, it would be a +1 times that wave function. So dxy should be in the G area, and we come over here and we see xy right there, dxy. And so that's going to be E2G. Bless you. So anyway, that's just something about the identifying the orbitals, the atomic orbitals in the character tables, in the G and U symmetry. What other questions do you have? Yes?
Could you go over question 12 from this homework? To the Boltzmann constant?
Okay. Which one? Okay, this one here? Yeah. Okay. So, yeah, so if we're looking at this, did you get 21? So it's asking, what's the Boltzmann factor for the ground state? Yeah, and so you can just look at this and you can see if it's in the ground state, then n equals 1. And so then this is calculating it for this, and it's comparing it to the ground state. So the ground state energy minus the ground state energy is 0. Anything raised to the 0 power is 1. So you don't have, that's why I say you don't even need a calculator. Just e to the minus 0 over kT, doesn't matter what temperature it is, doesn't matter what Boltzmann's constant is or anything like that. E to the 0 is 1. So that's why we end up with 1 right here. But for an electron in a 6.7 angstrom box at 100,000 Kelvin, what's the Boltzmann factor for the n equals 2 state? Okay, so n equals 2. So we've got to put this in. Okay, this is going to be, see if I can find, well, let's just go for it. So we need to, first we need to calculate the energy of the n equals 2 state. So E2 is equal to h squared n squared over 8ml squared. Let me just take this all the way to a blank page. see if we have a blank page at the end. Yeah, we do. Okay. So it's joules times seconds for Planck's constant. So let's go ahead, since we're going to have a mass here in the denominator and angstroms, let's go ahead and break that joule into the kilograms meters squared per second squared, okay, because we're going to need to cancel some units. I don't know if you've noticed, but a lot of the problems, the difficulty in the problems is just following the units, okay? So if you don't show your units, you're really hurting yourself, because that's how you can tell if you're getting the problem right or not. The units don't cancel, then you're dead already. Okay, so you've got to make sure the units cancel. So let's go kilograms meters squared per second squared, and it's Planck's constant, so that's the joule part, and it's times second. Okay, and that whole thing is squared. Okay, so but we're going to go ahead and take this second here, and we're going to cancel that with this exponent. Okay, so we've gotten rid of this times second, so it's kilogram meter squared per second for Planck's constant. Let's divide this whole thing by 8. And that's what's the mass of the electron. It's times 10 to the negative 31 kilograms. But what's the first number? I can't remember. 9.1. Okay, well, 9.1 times 10 to the minus 31 kilograms. Okay. Okay. And then we have 6.75 angstroms squared. Now we want to get out of angstroms and into meters. So this is a big issue here. So an angstrom is 10 to the minus 10 meters. Okay, so it's 10 to the minus 20 meters squared per angstrom squared. You have to not just square the meters and square the angstroms, you got to square the 10 to the minus 10 too. So 10 to the minus 10 squared is 10 to the minus 20. Okay. All right, so then we hammer our way through this problem. You should probably practice this on your calculator too. What's that? Yeah. So we can also check our work. Okay. I'm going to write intermediate values in here so you can see that. So for the numerator, I'm getting this piece here. I'm getting 1.75. I'm running out of space on my window. Okay. Let's write over here. 1.756 times 10 to the minus 60. And then that's meters, it's kilograms squared, meters to the fourth over seconds squared. Okay. So you can check your work on that and compare it to my numbers. Let me know if I've made a mistake. All right, so then in the denominator, I have 8, enter, 9.1, 31 times 6.75. Squared times Okay, I'll have to check my work. 20 minus times. All right, so for the denominator, I'm getting 7 times 10 to the minus 48. And so let's see what the units are on this one. So I've got kilograms. The angstrom squared have canceled, meter squared. And this is beautiful because my kilograms going to cancel this square up here. My meter squared is going to take away 2 of those meters, or the meters to the 4th, and I'm going to end up with kilograms meters squared per second squared, which is a joule. Hey, that's great. That's what we want. Okay. Okay. And so let's swap those and divide. You said minus 66? So let's see what I did wrong. Yeah. 66. 1.756, okay. And then 3. So I get a really small energy, as you might imagine, 5.29 times 10 to the minus 19 joules. Okay, does it, let's see. Let me go back to the problem. Does it give us the ground state energy, or do we have to calculate that too? Yeah, we got to calculate that too. Okay, fair enough. Oops. Okay. Yeah, we can divide that by 4. So this was for n equals 2. This is, so then E for n equals 1 will be 1/4 of that. Okay. 2, 3 times 10 to the minus 19 joules. Okay, so those are our 2 energies. For the Boltzmann factor then, over KT. Yeah, we're dealing with singly degenerate energy levels in the particle in a box. So there's no change in the degeneracy all the way up. Okay, I'll put it in here, and so I'll say G sub n is equal to 1 for all 1D PB problems. So 1D particle in a box. All right, so then we end up with e to the minus 5.29 minus 19. Take a difference. All right, so then what's Boltzmann's constant? 3.28, 2.38, going from memory. 1.38, okay. Boltzmann's constant, 1.38 times 10 to the minus what? 23? Yeah, 23. Joules per Kelvin. And that's multiplied by temperature to get out of that joules per Kelvin and just into joules. So 100,000 Kelvin. Okay. 1.38, sorry. I get 0.75. So compared to the ground state, which has a Boltzmann factor of 1, this n equals 2 state at 100,000 Kelvin has a 0.75 Boltzmann factor. It's like 75% of the chance being in the second excited state that you have than you have at the first excited state, or the ground state. So you see at this temperature it drops off, to 75% chance of being in the next excited state. Now, if you wanted true probabilities, you would take up all the possibilities and put that in the denominator, and then divide each of the factors by the denominator to get, because right now, like 1 and 0.75, if you add those up, you don't get 1. All your probabilities should add to 1, right? A probability of 1 is a sure thing. And if you say, what's the probability of being in any level, it ought to be 1. What's the probability of being in any particular level, ought to be less than 1. So these are unnormalized probabilities. They're just all relative to the ground state. So whatever probability you have of being in the ground state, these are relative probabilities to that. Okay. So we'll get into all of that. That's called statistical thermodynamics, and we'll get into that in the spring course if you take thermodynamics. We'll take the Boltzmann factor and we'll normalize it by adding up all of the probabilities of all of the states. And so the sum of all of the Boltzmann factors is in the denominator, and then you get true probabilities. So it would be at a certain temperature, maybe a 40% chance of being in the ground state, and a 38% chance of being in the excited state, and a 20% chance of being in the third state, and so on. But all of those probabilities would add up to 1 once they're normalized. So what we have here is just unnormalized probabilities. So it's kind of a tedious problem, but it's a homework problem, right? This would be kind of a long one for an exam because of all of the things. Now, you could simplify this a little bit by multiplying this number by Avogadro's number. So if you multiply this by 6 times, oh gosh, my handwriting is terrible today. I'm trying to go too fast. 6, all right. So 6.022 times 10 to the 23rd per mole. Then you end up with joules per mole. Okay. And then you would have this one, and it would be a nice, neat number because you got 10 to the minus 19 and 10 to the 23rd. And so this is really, I've built this system with such a small box length that we get real nice numbers in kilojoules or joules per mole. Okay. You would do this one also times Avogadro's number. And then when you get to the Boltzmann thing, this number here, Boltzmann's factor, 1.38 times 10 to the minus 23 joules per Kelvin times Avogadro's number to the positive 23 per mole gives us some interesting units: joules per mole Kelvin, and the number is one that you might recognize, 8.314. So it's the gas constant. So R is just Boltzmann's constant times Avogadro's number. And so you've used that number quite a bit throughout science, probably in physics, probably used it in Gen Chem when you get to the ideal gas law and so on. The R value in the ideal gas law is just this factor here converted over to liters, atmospheres per mole Kelvin. So you've been using Boltzmann's constant all this time and didn't know it. So that's kind of cool. Back to the homeworks. I did put a couple of questions on these potential electrostatic potential maps. And so we kind of got we ran out of time when I talked about it in lecture, and so I wanted to just emphasize this again. So the volume that's being taken up by this figure, don't look at the colors, just look at the shape of the cloud. That's the electron density. So the total electron density is given by the volume of that electron cloud, right? And so then we go around and we test how positive and negative that is. So you've got a nucleus inside that electron cloud. How much of that positive charge does the electron cloud hide? Because if it hid nothing, you'd see a very positive part of the molecule. If it hid it really well, then you'd see a negative part of the molecule. Okay. So then we color code it. So positive is blue and negative is red. Okay. So right here, what do we see? Well, we've got these OH groups. So this is an OH group. So where the H is positive, where the O is negative, as you might imagine. So, you know, oxygen has a lot of electrons. You got a proton stuck on it. That proton is somewhat acidic. The more positive it is, the more acidic it is. So these electrostatic potential maps can explain things like pKa's, how strong an acid is, so on. Also explains where, you know, an electrophile or a nucleophile will attack. Okay, so like right here, that who knew that proton? I mean, everybody knows an OH, the H is going to be slightly acidic, depending upon what it's bonded to. But look at that proton there, or that hydrogen. Is that the alpha hydrogen? What's that? Is that the alpha hydrogen? Yeah, for this group. So that's, you know, that's. And we see that, like if this was an aldehyde, that alpha hydrogen from the aldehyde is pretty acidic and it can be stolen. So this is the beauty of Gaussian, is you can get these kinds of things that explain your organic chemistry reactions. So this is the stuff you had to memorize in organic can be explained here by looking at the electrostatic potential map. So that's really pretty slick. So if you're given a molecule, which you will be on the exam, here's this molecule, look at it. Tell me where the positive region would be. Tell me where the negative region would be. It's going to be something easy. Okay. And so I'm not going to give you like this weird one where HF and lithium hydride, right? But because you can't see the atoms in there. But if you could, you know, what we have here is we've got H on this end bonded to fluorine. And here we have lithium on this end. What did I do that for? My hand is not behaving. Lithium bonded to hydrogen. And so this is really strange. Right here, this is a hydrogen that's negative when it's bonded to lithium. And that's why we call it hydride. What does that IDE tell us when we say chloride, when we say fluoride? What are we thinking? We're thinking anion, right? And so here, hydrogen's acting like the anion, and lithium's acting like the cation. Okay, it's still a molecular substance. It's not quite ionic bonding, but it's definitely unequal sharing. Here's H2, total equal sharing, totally covalent, right? Those electrons don't know which nucleus they belong to. Okay, but over here, hydrogen is stealing all the electrons from the poor old lithium, even though the lithium's got 3 protons. But still, why that happens, I don't know. But the HF here, you know, the fluorine is going to pull the electrons away from the hydrogen. So this is, again, something that can explain why hydrides and fluorides have different chemistry. Here's water, and here's methane. So methane, not very acidic, right? Those hydrogens are green. Ammonia and water acts as an acid and a base. It can donate protons, it can receive protons, so it's amphiprotic. So here's HI. That cloud is so big, you can't really even see the exposed hydrogen, and it's not very negative because, again, what makes something really negative is a tightly localized ball of electrons. So the iodine, it's just not the electrons are spread out so far that it's really not a strong concentration of electrons in any one spot, so it's not very negative. Whereas HF, what? So large? Yeah, it's a size effect. Yeah, and so then, but HF, you got a little tight ball of electrons on the fluorine and an exposed proton, so it's very, very acidic. Okay. You feel better? Yes? Yes, last question. Pardon? There's not a lot. So look at that one on Monday. I did the transition equation where you have like a e to the n plus 1 or e of n plus 1 minus e of n, and you just put those in and then do the algebra. There's one of those for sure. And then using the energy equation, like if I gave, like in this question, we had the mass and the length of the box and we're asked for the energy. What if we're given the energy and asked for the mass of the particle? What if we're given the mass of the particle and the energy and asked for the length of the box? So be able to work with that energy equation forwards, backwards, sideways, okay? And just you just got to yeah. So yeah, no carb for sure. So but you still got to pay attention to your units and your times 10 to all those powers, you know. Yeah. Wish you the best. Go watch that video for today. You can wait till after the exam, but Friday then watch that video that we were going to do today on the vibrational spectroscopy. Okay, that's our understanding. If we do a review session here, then I'd like for you to make it up by watching that video.